In this course, we will cover nanoPower. We will discuss what nanoPower is and how to achieve it. So what is nanoPower? We define nanoPower as a device with a quiescent current less than 1 microamp, basically nanoamps. It can be a very strict definition. This allows us to categorize our products, but it doesn't tell the whole story about nanoPower. Nanopower can be thought of in many ways. Here's how. Nanopower is a technology, one that enables new applications, many of which we will explore today. Nanopower is a new set of devices, or a tool set. If we look at any class of devices, they are always optimized for certain types of performance, be that efficiency, noise, speed, etc. In the case of nanopower, these devices are optimized for quiescent power consumption. In this case, you have a new set of tools that you can apply to designs that require ultra-low quiescent current. A set of features that minimize current consumption. Nanopower is not one single feature or design trick. In the case of our nanopower devices, we have put a number of features in that reduce current consumption. Through the course of this discussion, we will explore a number of these. In aggregate, you can see the benefits. Finally, nanopower enables certain functions for virtually no energy at all. Consider a device that operates with a quiescent current of 30 microamperes. Placing a 125 nanoamp supervisory device on the circuit is basically energy-free. There's no impact on the overall energy budget. As a design engineer, you still need to consider space and cost, but from an energy consumption standpoint, you can view this feature or function as energy-free. Let's look a bit more into the manifestation of quiescent current. In a DC to DC switching regulator, quiescent current, or IQ, is the minimum amount of current for the converter to stay alive when it's not in use. No switching, no load, but enabled. It is the nominal current used while on in a minimal state. The IC is turned on and ready to work. All of the IQ simply travels inside the IC to ground. There have been a lot of questions raised on the difference between quiescent and shutdown current. They can be confused from time to time. Shutdown current is when the device is asleep and not ready to work, while quiescent current is the nominal current used while the IC is resting and ready to work. The system is in an idle state and waiting for something to happen. Designers usually use quiescent current to gauge the power dissipation of a power supply at light loads, and use shutdown current to calculate the battery lifetime if the device is turned off, yet the battery remains connected to the regulator. Real-world application examples include when the charger is not charging the phone but still plugged into the wall, or when a wireless mouse is not in use but not yet switched off, or when a car is turned off but the head unit is still running. In many battery-powered applications, it is the current drawn from the battery in a standby condition with a minimum load to drive. As we look at industry trends, we see more and more devices that require or can utilize nanopower. On the left, we see smaller and smaller devices or sensors. We'll dig into how nanopower devices can reduce the size of a battery or system power supply, enabling those entire devices to get smaller. On the right, we have a very interesting application of an internet-connected door lock. In this application, consider how infrequently a door lock actually operates, perhaps something like 10 or 20 times per day. If we actually think about the time that the shaft is moving, divided by the time of the entire day, the duty cycle of this device is extremely low. However, that door lock must work when we need to open the door. So the key here is that operating devices can be in standby mode for a long time, but need to operate at critical times with long battery or power supply lifetime. There are three critical points that illustrate nanopower's importance. First and foremost, extending battery life. Secondly, nanopower enables a decoupling of functions, allowing for improved system performance. This flies in the face of our conventional thoughts and the trend of integration, but it is a real phenomenon worth understanding. Finally, nanopower allows for enhanced system control. Some examples of how nanopower can be used to provide more control and safety in a system will be shared in later slides. So, if we are talking about ultra-low power, we need to think about new energy sources, most commonly referred to as energy harvesting. Energy harvesting comes in many forms. Most commonly, it consists of using mechanical, photonic, or heat energy to generate electricity. Clearly, for a nanopower or ultra-low power device, this would be a great area to explore. One effect that we consider in nanopower applications is battery self-discharge. Self-discharge is a phenomenon in batteries in which internal chemical reactions reduce the stored charge of the battery without any load connected between the electrodes. Self-discharge decreases the shelf life of batteries and causes them to initially have less than a full charge when actually put to use. Other factors affecting self-discharge are how the battery is stored, humidity, and most importantly, temperature. Here we see a chart of a lithium-ion battery and its rate of discharge for various methods of storage. In all cases, you see a self-discharge on the order of millivolts per day. Let's take a closer look at a variety of battery chemistries, each of which has a different self-discharge rate. We are looking at general or average discharge rates. Overall, batteries lose some percentage of charge over time. Some see an acceleration early on, such as nickel and lithium-ion chemistries. Also, a ton of work has been done to reduce the self-discharge rate of primary cell alkaline batteries, since they need to be able to sit on a store shelf for a certain amount of time. Let's look more closely at one of the smallest batteries you can get. This is a CR1216, which is 12.5 millimeters in diameter and 1.5 millimeters thick. It holds 34 milliamp hours of energy from a terminal voltage of 2 or 3 volts. On average, this battery will self-discharge the equivalent of 39 nanoamps of load current in a year, or over a 10-year period, 390 nanoamps. For nanopower, if you want to power a really small device, this can become a significant amount of energy. Now, what is more important to consider in the context of nanopower is how our circuits can compete with battery self-discharge. If our circuit quiescent current is 10 times or more greater than battery self-discharge, then we are accelerating the drainage of our batteries. If we can design a circuit that consumes, in standby mode, a current on the order of the battery self-discharge, then we're not accelerating battery discharge, we're maximizing battery life and pushing the problem outside of the circuit to the battery. Let's look at how quiescent current impacts the standby life of this battery, the CR1216. A simple calculation shows that reducing quiescent current from 4 microamps to 1 microamp will increase system standby life by almost 3 years. This provides the opportunity to run a system longer or to shrink the size of the battery and hence the size of the system. Increasing battery life is so important in so many additional ways. Extending battery life and/or reducing battery size opens up many opportunities to build products in new form factors. This image is a tiny biosensor that can measure blood chemistry when placed in the body. Later in the discussion, we will touch on different applications from each of these end equipment segments: medical, consumer, industrial, showing how the benefits of nanopower can extend to a variety of systems. An additional benefit of extending battery life is reducing system maintenance to replace batteries. Many products are in hard-to-access areas, such as on roofs or in basements. Access can be costly and require trained professionals. Utilities, for example, call maintenance events truck rolls, anytime they need to roll out a truck to fix or maintain a system, such as a meter or a grid disruption. Reducing the occurrence of these events is a bottom-line saver. Nanopower also allows what is called a decoupling of functions. The example here is a wearable device. In the device on the left, the microcontroller with an integrated real-time clock, or RTC, runs at 250 nanoamps in the lowest standby state. Now, micros can go lower, but they're in shutdown. Many of these devices need to maintain time for various housekeeping functions. By taking the RTC out of the microcontroller, a quiescent current of only 180 nanoamps is possible, a reduction of over 25%, enabled by eliminating any overhead from the microcontroller. Another example is power management ICs, or PMICs. PMICs became extremely popular during the advent of digital cameras, and especially smartphones. They contain a big switching power supply, maybe more than one. They also have a bunch of LDOs, GPIOs, maybe a battery charger and/or a fuel gauge. The idea behind PMICs is to integrate as much power management into a single device as possible. PMICs, as one can imagine, carry the quiescent current payload of all the functions that they utilize. So you are adding up the quiescent currents of the switcher, battery management circuit, etc. While many of those functions can be turned off, PMICs will always have a greater payload. Many designers are therefore using smaller PMICs with one or more nanopower regulators to manage power from a battery, or produce a higher voltage to drive an LED. Again, this disintegration provides a major system benefit. Another benefit of nanopower is energy-free enhanced system control. Here we have two examples. One is a comparator monitoring the voltage of a battery. On the other side, we have a supervisor/watchdog part monitoring a microprocessor. In these instances, the comparator runs off of 900 nanoamps, and the supervisor runs off of 125 nanoamps. If the quiescent current of these systems is in the range of tens or more microamps, then the overall impact of these functions is negligible in the overall energy calculation. These functions are energy-free, and the energy cost can be eliminated from the overall energy budget calculation. Now, you still need to consider both board space and cost, but from an energy standpoint, these functions are energy-free. We've also seen these functions are really valuable in many applications. There have been many instances of batteries overheating and even exploding in portable equipment. Adding a simple comparator provides low-cost insurance for monitoring the supply and making sure that if the battery goes out of a safe voltage range, evasive action can be taken. The supervisory part also provides that type of insurance against software bugs that result in never-ending loops. The watchdog may be placed into a system with little to no software or firmware modification. If the system goes into a never-ending loop, the watchdog resets the system, providing more reliable operation and robustness against bugs. NanoPower is a result of many small actions. First, turn off everything that can possibly be turned off, but not everything. It is important that a system remain in a state where it can quickly take action from its quiescent state. But in that state, we turn off every function that we can. Secondly, use ultra-low power building blocks. From a chip design and current consumption standpoint, not all building blocks are created equal. To achieve nanopower, one needs to work from the set of building blocks that are available. From a technology standpoint, some blocks are simply not there yet in terms of achieving nanopower. Reduce losses in the feedback network. Where a classic resistor divider is used to measure a voltage, current is constantly being drained to ground. There is another way to eliminate that current drain, by running a current through a resistor during startup only to measure and set that value in the chip. Lastly, diodes create losses in a system due to their forward voltage drop, and we'll discuss some techniques for eliminating that loss. Here is a list of products and building blocks that make good candidates for nanopower. They are DC to DC converters, supervisors, comparators, current sense amps, op amps, real-time clocks, and microcontrollers. One interesting way to achieve nanopower is to eliminate losses from a feedback network or resistor divider. We've designed a new interface called Resistor Select, where a single resistor gets connected between ground and the R cell pin to set a value, such as output voltage. We run a current through the resistor to determine its value and set that value in the chip. This event is only done at startup and consumes no current ever again until the part is shut down and restarted. We can measure up to 33 different resistor values. For more flexibility, vendors typically provide a resistive feedback string to allow designers to customize the output voltage. This is so the same part can be used for multiple purposes without having to stock a different part for each application. This network requires two resistors providing feedback to set the output voltage. This type of network always drains current from the output no matter whether the system is at shutdown, active, or standby. This is problematic for ultra-low power applications where every nanoamp saved is important. Let's say we want to set the output voltage of a device with a feedback network to 5 volts, and we use high-value resistors of 10 megaohms and 30 megaohms. Even with those high values, there would always be 125 nanoamps leaking to ground. The nanoPower Max 17222 boost converter has a unique single resistor output selection method known as R cell. At startup, the part uses up to 200 microamps to read the resistor value, and it only takes about 600 microseconds. After reading the value, the cell pin does not drain any current during operation. Here's a view of the R cell in action for one of our boost converters. During startup, you can see the Vout plateau. This is the time period in which the part is measuring the resistor. After the measurement, the part ramps up to the appropriate voltage and the process is complete. In this case, it takes about 700 microseconds. Another common energy loss in systems, especially when using multiple power supplies, is a drop across a diode. This drop tends to be about 0.7 volts, so your loss is the forward voltage drop times your quiescent current. In this instance, we've put our DC to DC boost converter in place of the diodes. A shutdown feature in our nanoPower converter allows the voltage drop across the diode to be eliminated while still performing the diode function of preventing current from flowing upstream. In an example calculation, we estimate an improvement of 18% in battery life for two AA batteries running in a 3 microamp quiescent state for a 3% duty cycle system. Of course, benefits will vary depending on how much current is required to drive the enable pins and how the micro is used to drive them.
To summarize, in this course, we have covered what is nanoPower and how to achieve it. For more information on this topic, please go to our website at www.maximintegrated.com and search for nanoPower. We hope you enjoyed this video and see you again in another educational video of Maxim Integrated.